Okay, so we are talking about the equivalence between the 𝜖-NFA and the regular expression. So, last class we have given the statement of the theorem, given a regular expression R, there exists a NFA 𝜖-NFA M such that the language of the regular expression M accept such that M accepts L of R. In particular, the language of M is same as language of R. So, this theorem we are going to prove by induction on the number of operator on R. Okay. So, to prove this theorem, we will use mathematical induction on the number of operators in R. R is a regular expression. So, which consists of some operator, like there are only 3 operator, concatenation, plus and star. Okay. So, we will prove this by mathematical induction on the number of operator on R. So, in that case, what is the base case? Base case means where number of operator is 0. That means, so you just recall the definition of regular expression. In the definition, we recursively define the regular expression. There is a base case. We define this epsilon, then MT and A, where A is coming from the sigma. These are all regular expression with 0 number of operator. This is the starting, and the recursively we define the regular expressions. How? Suppose R1, R2 is a regular expression. R1, R2 could be one of this. Then, if R1, R2 is a regular expression, then R1 plus R2 is a regular expression. Then R1 into R2 is a regular expression. R1 star is a regular expression. So, now what are the language corresponding to this? So, this will corresponding to the language of R1 union language of R2. This is language of R1, language of R2, and this is language of R1 star. This we all know. This is the recursive definition of regular expression, and the base case is what is the language corresponding to this? This is the singleton set epsilon, and this is empty set, and this is the language corresponding to the singleton set A. So, this is the definition of regular expression. Now, these are operator, this is concatenation, this is plus, and this is the star. Okay. So, now we will prove this on the by using the mathematical induction on the number of operator. So, for that let us first prove the base case, because every mathematical induction method we have a base case. We prove the result is true for n is equal to 0 or 1, that is the base case. Now, after that we assume the result is true for n is equal to k up to k, and then if we can prove the result is true for k plus 1, then we are done. So, that is the way we will do this. So, base case. So, base case is number of operator is 0. Okay. So, there are 3 base case. One is epsilon is a regular expression, which is denoting the language of this is singleton set epsilon. So, this is now we want to find a automata for this, which is accepting this. So, what is the automata? This is q 0, we have q 0. So, this is our M. This is our M such that L of M is nothing but epsilon. Okay. So, it is only accepting epsilon. This is a epsilon NFA, although there is no epsilon move over here, but this is a automata and this is a epsilon NFA. Epsilon NFA, it is not mandatory to have a epsilon move. We can have a epsilon move, we may not have a epsilon move also. In fact, there is no move on this. So, that is why it is accepting, and this is the starting state, is also the final state q 0, that is why it is accepting the epsilon. Okay, number 2, empty. So, what is the language of this? It is just a empty set. Now, what is the automata for this? We can have automata like this q 0, and we can have final state q 1, which is not reachable from q 0, that is all. This is our M, okay, which is not reachable from q 0 by any move, any means, even not by the epsilon move. So, L of M is empty. Okay. So, this is, now we have another base case number 3, which is the regular expression A, where A is coming from, where A is an any alphabet coming from that sigma, our set of all possible finite alphabet. Okay, so, what is the language of A? Language of A is the singleton set A. Now, what is the automata? Simple, we start with q 0, q 1 is the final state, we have a A. So, this is a NFA, in particular this is a epsilon NFA. Okay. So, this is our M. So, L of M is A. So, the result is the theorem, the statement is true for 0, the base case, that is the number of operator is 0. Okay. Now, the inductive step. So, these are all the base epsilon NFA for the base case. Now, the induction. So, one or more operator, more number of operators. Okay. So, we assume that given a regular expression having one or more number of operator. So, they are not the base case. So, they are, so in that case they are either of this form, if R is such a regular expression which is having that okay. So, for that we need to have a assumption or hypothesis, the induction hypothesis or assumption. We assume that the theorem is true for a regular expression R with fewer than I, where I is greater than or equal to 1 operator. Fewer than I, that means the result is true for up to I. Then we have to show, this is the assumption, this is the induction hypothesis. Then we have to show that if our result is true for I, then we are done. So, result is, that means it is true for the all k up to I. Okay. Now, we have to prove using this induction hypothesis, we have to prove that the result is true for I is equal to k is equal to I. If we can do that, and we have already have the base case, result is true for I is equal to 0. So, if we can prove this, then the result is true for I is equal to 0 plus 1, that is 1, I is equal to 1, I is equal to 2, I is equal to 3. So, result is true for all I, but with the help of, so this is the induction hypothesis, this is our assumption. Okay. Now, we assume this result is true for all regular expression whose number of operator is less than up to less than I. Now, we take a regular expression with number of operator is I, and then we will see whether we can construct a 𝜖-NFA for that or not. So, let us try that, and this assumption we need. So, let R be any regular expression with I number of I operator. And here I is greater than 1. So, if I is greater than 1, it is not the base case, then R must consist of the recursive definition. So, R will be of this form. There are 3 cases are here. Case 1. So, R will be either some R 1 or R 2, where both the R 1, because we have used one operator over here. So, then R 1 and R 2 are both are. So, number of operator in R 1 and R 2 are both less than I. And case 2, R may be R 1 concatenation R 2, where number of operator in R 1 R 2, because we have used one operator, that is called concatenation, or it is a unitary operator, R is some R 1 star. So, we have used one operator. So, in that case the number of operator in R 1 is less than I. Okay. So, these are all less than I. So, on the if it is number of operator in any regular expression is less than I, then we have a assumption or we have a hypothesis that we have a 𝜖-NFA for that. So, that means we have 𝜖-NFA for R 1 and R 2 for each of these cases. Now, from that we need to construct 𝜖-NFA for R for each of the cases. Okay. So, let us try that. So, let us try one by one. First, we will take the case 1. Case 1 is R is R 1 plus R 2. Now, R 1 plus R 2 number of operator in R 1 and R 2 are both less than I. So, by the using the hypothesis, the assumption, our assumption, in that case we have a regular expression M 1, we have 𝜖-NFA M 1 and we have 𝜖-NFA M 2 such that L of M 1 is L of M 2 is, this is by induction hypothesis or the induction assumption. That is the assumption, because this if R is having I number of operator, we have used one operator. So, R 1 is will be having less than I operator and R 2 must be having less than I operator. Once it is less than I operator, then we have a regular we have 𝜖-NFA for this, which is accepting this, and we have 𝜖-NFA for this, which is accepting this. Okay, now, from here how we can have 𝜖-NFA for R, how we can have 𝜖-NFA which is accepting the L of R. Okay, so, let us try that. So, suppose we have M 1. So, suppose M 1 is like this, we are starting with some Q 1, and then say Q 2. Okay. And then, so this is say not Q 2, they are Q F 1, M 1, Q 1, F 1. So, that two steps. So, this is the final state. So, this is the starting state like this. So, this is suppose M 1, this is our M 1. So, this is the 𝜖-NFA for R 1, that means any string of L of R 1 will be accepted by this. So, if you start with that q 0, q 1 it will be reached to the. So, if you take any string from L of L 1, then from q 1 if we start x will goes to f 1. So, this is the way. Okay, good. So, now this is the M 1. Now, corresponding similarly we have M 2. For M 2 we take q 2 and then we have a final state f 2. And here we are assuming the only one final state for each this, and there is no move from this final state to any other state. That assumption is there in the theorem. Yeah, so that assumption is there. So, we are assuming we are going to construct 𝜖-NFA which is having only one final state and there is no transition from this final state. Okay. I mean this assumption is not required, but to make the proof simple we have to do, otherwise we can have, because if you have many final state we can have different construction for this. But anyway we can have, because the base case we are not violating this assumption that we have only one final state and there is no transition from the final state to any other state. Okay, good. So, now this is also M 2. Now, if we have a y which is L of R 2, then so if we start from q 2 with this y we can reach to f 2. Okay. So, this is by the induction method. So, we do have a 𝜖-NFA for R 1, we do have 𝜖-NFA for R 2. Now, the question is from here how we can construct 𝜖-NFA for R 1 and R 1 plus R 2. So, that is the construction we are going to do now. So, we are constructing a new 𝜖-NFA with the help of by taking. So, we have this M 1, this is this is not a single, there are many states over here F 1, this is our M 1 and we have M 2 also, Q 2, F 2. Now, we have a Q 0, this is we are constructing the new M which is which could accept the R which is R 1 plus R 2. Then this is F, new F. So, we have a epsilon move from here to here. Then we have the move for M 1. Then from here to here we have epsilon move. From here to here we have epsilon move. And this is our final state. And this is our starting state. Okay. So, this is our M. So, this is the 𝜖-NFA which is accepting the language. So, this is our M. So, L of M is nothing but L of R 1 union of L of R 2 which is accepting the language L of R 1 union L of R 2. How to show this? Because if you take any x from L of R 1, then what we do? We first start with this, we take the epsilon move, we go here, then x is a accepted string, then with the x we will go to the this thing f 1, then from f 1 with the take of help of epsilon move we go there. So, like we start from q 0, then by epsilon move we will go to q 1 and then with this x we go to f 1 and then again by epsilon move we go to final f. This f is our the final state. There is only one final state, that is the part of the theorem done. Now, similarly, if you take a y from here we take this path we go there. Okay. So, this L of M is basically, so any element here, and similarly we can, this is equality. So, if we have, if there is a if there is a string which is accepting by this new NFA, then it has to go either this path or this path. Now, if it is going to this path, then it has to reach to x f 1 final state of this. So, that means that string is accepted by this M 1 or it has to reach to this, that string is accepted by this. So, this is a subset of this, that is a subset of this. So, from here we can say this is equal. Okay. So, we can formally define this M with the help of tuple, like if say M1 is Q1 and Q, this is small q1, sorry, delta 1 is the transition, small q1 f1. So, if this is M1 and q2 sigma 2 and sigma 1, this could be same or this could be different. We are taking the general one. So, we can make it different. Then what is our M? M is nothing but q sigma delta q0 and f. So, what is sigma? Sigma over what is q? Q is nothing but q1 union q2 and sigma is nothing but sigma 1 union sigma 2 along with the epsilon, and q0 and f we have introduced the new state for this. And what is delta? The transition delta of q comma a is equal to delta 1 of q comma a if q is in q1 and a is in sigma 1. That means, if we take this path, we will follow the transition rule of M1. If we take this path, we will follow the transition rule of M2, and similarly this, and we have 2 epsilon move over here. So, delta of q0 epsilon is nothing but q1 and q2. Okay, and there also we have epsilon move, delta of f1 epsilon, which is f, similarly f2 epsilon, which is also f. So, anyway, formally we can define this formal thing will be available in the lecture note. This is case 1. So, then this is the M which is accepting the, so this is the M which is accepting the, so that means it is corresponding to, so this is nothing but language of, okay. So, this is the proof. Now, we take the other case, case 2. Okay, case 2. Case 2 is the concatenation. R is nothing but R1 R2 concatenate, and we assume there is a because of induction we assume there is a epsilon NFA for R1, there is epsilon NFA for R2. Now, we need to construct a epsilon NFA for R1 R2. Okay, suppose this is the epsilon NFA for R1 Q1 F1 and this is the epsilon NFA for R2 Q2 F2. So, this is our M1, this is our M2 such that these two are accepting this two regular expression, regular language. I mean the language corresponding to these two regular expression. Okay. Now, how to construct a new NFA, epsilon NFA? We do this, we take the starting state of M1 as the starting state of M, then we have epsilon move from here to here and this is our final state. This is our final state. Okay. So, this whole thing is our M. So, then what is the language corresponding to M? Because if so L of this is nothing but x y such that x is x is L of M1 and y is L of M2. It can easily verify, because if we take a x y the string, we take start with this, then with the x we reach to the f1, then from there we take a epsilon move, we go to q2, then with the y, because this is nothing but x epsilon y, x y can be written as x epsilon y, epsilon is a null string. Okay. Then with the help of this we will go to the final state q2. So, f2 is the final state of this. Okay. So, now here also we can have this formally we can define this M with the help of M1 and M2. So, if M1 is Q1 sigma delta 1 Q1 and F1, if M2 is Q2 sigma 1 sigma 2 say, I mean we could take the same or different, because if it is same also does not matter, we can take the union of that and then, but anyway for generalized case we are taking these two are different, and Q1 and Q2 we are taking they are disjoint in the earlier case one also, because if there is some state we can easily rename. So, we can always assume that this Q1 and Q2 are disjoint, because by renaming of the states, this one delta 2, then Q2 F2, then what is our M? So, M is nothing but Q1 union Q2 sigma 1 union sigma 2 union epsilon delta, then Q1 and then F2. And what is delta? Delta is nothing but, so delta of QA is nothing but delta 1 of QA if Q is in Q1 and A is in sigma 1, including epsilon, and otherwise it is Q2 QA if Q is in Q2 and A is in sigma 2, and we have epsilon move over here, delta of f comma epsilon is Q2. Okay. Because there is no other move from these states. So, that is one of the assumption, that is one of the part in the theorem. Okay. So, this is done. So, this is the second case. Now, in the next class we will prove the third case and then we will take some example. Thank you.